Hello my dears, very good morning to all. Today we are going to discuss about a very important session in measurement, which is nothing but electro dynamometer type instruments. Electro dynamometer type instruments. Electro dynamometer type instrument. So this is the simplest picture of the electro dynamometer type instrument. It can be used for both AC and DC. I will explain why it is. And mainly it consists of two coil. One is current coil, and which is connected in series with the load or series with the supply, and divided into two halves. And next coil is called pressure coil, or pressure coil's other name is called moving coil, or current coil, other coil is called fixed coil. Okay, current coil equal to fixed coil, pressure coil equal to moving coil, where MC is equal to moving coil, and connected in parallel with the supply. And of course the current coil current I1, which is depend upon the load, and because this instrument now my dear, this is not it is the principle, but it can be utilized with either wattmeter, either voltmeter, either ammeter, either ohmmeter. Now that type of instrument can be, in that instrument this principle can be accommodated. Okay, so without a load connected, I am showing the picture. Okay, so there are two type of coil simply, but pressure coil or the potential coil or called moving coil. This coil is supposed to move, and another coils are fixed coils. So the fixed coils is divided into two halves. One half here and one other half is here, and the moving coil is nothing but that which is connected directly across the supply, and fixed coil is nothing but which is connected across the load. So, and one more thing, fixed coil or what, current coil, fixed coil or current coil having what, fixed coil or current coil having thick, less number of turn, low resistance, low reactance wire, or simply low resistance wire, comma, reactance depends upon load. Is it correct, my dear? This is nothing but the fixed coil is very thick coil. And because why it is thick? The fixed coil is always thick. Why? Because it has to carry the load current. If the fixed coil is very thin, what happen? If the load increases, load current also increases. Then what happen? The coil may burn, because its cross sectional area is very less, means it can't carry more current. So what happen? The coil may burn. So in order to avoid that, always the current coil now the name is fixed coil here, but generally the current coil is very thick and few number of turns, if it is very thick means we can't make very high numbers, right? We can't make very number of turns, right? Only few turns you can make because it is very thick. So you can't coiled it to very number of turns, correct? So this is the fixed coil, current coil matter. And moving coil or what, pressure coil or potential coil is thin wires, many number of turns, high inductance, and high reactance, high resistance. high inductance and high resistance. So the moving coil or pressure coil is directly connected across the supply, which is very moving in nature, so that it is very light and it contains very many number of turns, large number of turns, many number of turns in the sense large number of turns, and it is high inductive. It is high inductive means in the sense if the number of turns is increases, L is equal to N phi by I na. We have the relation L is equal to what, my dear? N phi by I. If number of turns increases means of course it inductance will increase. When inductance increases means, or when the number of turns increases means phi also increases. Or in short, overall what happens, my dear? Inductance will be increased. That is why this moving coil or pressure coil having high inductance and high resistance. Since why the resistance is very less? Since we are using very fine number of turns, its area of cross section will be what, my dear? Rho L by A. Since we are using very fine number of turns, its area cross section decreases, so that R will be increases. And here the N will be increases, so that L will be increases. That's all simple. Okay. Is it clear, my dears? Is it clear? Did you note this? So that's all about the two coils, and I will tell you the working. So the working principle of this electro dynamometer type instruments are they are simply when the two currents interact, my dears, when the what, or simply what, a coil is situated in a magnetic field, a current carrying conductor situated in a magnetic field, what happened? There will be a force, or there will be some force experienced by that current carrying conductor. Now this moving coil, my dears, this is situated in the field between these two fixed coil, or the field due to this fixed coil, this is acting along, or this is acting on the moving coil, so that there will be a force or there will be a torque developed. We just need the equation of torque, not the derivation. If I do the derivation, it will extend 3 pages at least, because you have to convert the whole system into self-inductance and mutual inductance terms, and you have to do very long mathematics, then only it will get the answer. But for examination point of view, our examination point of view, we don't need that derivation. We just need the deflection torque, my dear, TD equal to I1 into I2 into dm by d theta, where m is the mutual inductance and theta is the deflection or deflecting angle. Theta is the deflecting angle. So this equation, this only you have to learn. TD is equal to I1 I2 into dm by d theta. Now we are going to deal with what happened when AC is fast, what happened when DC is fast. So first case, when DC is passed. So what happened, my dear, when DC is passed? We have TD equal to I1 into I2 into dm by d theta. Okay, so suppose let I1 equal to I2 equal to I. From the figure itself, it is very clear that the same current I1 is going through as I2, and it's again same to as I1, I2. Just I marked 2 names for the current coil representation as well as the pressure coil representation. That means the pressure coil, the current carried by I2, the current coil, see my dears, both the current coil carries the current I1. For that, I will what is the significance of mentioning these 2 quantities like I1 and I2? It will clear when AC is passed. Okay, so as far as now, when DC is passed, I1 equal to I2 equal to just simply I, so that TD will be equal to I square into dm by d theta. I square into dm by d theta. Okay, and you have a doubt that there is any mutual inductance in DC also? Of course, because the coil is turned, my dears. The coil is in spiral manner, so that there will be, of course, there will be some magnetic field associated with, and it is Also what the flux is induced, the flux is induced in it, there will be some mutual inductance also, there will be some mutual, because see I will tell you one example. Suppose you take a coil like this. Suppose this is the coil. You take a nail wound over the nail. That means the coil, you have a coil, please wound it over the nail and apply a battery across its terminal and bring it near to the pin, safety pin and all. It will attract. Why? It produces a magnetic field. It produces a magnetic field, my dear. DC also produces magnetic field. DC also having some source, forces. DC also has having some forces. So definitely TD will be equal to I square into dm by d theta. So what happened? The deflecting torque directly proportional. I can write like deflecting torque directly proportional to I square. Is it clear, my dear? Here we are using spin control. Here we are using, since we are using spring control, theta proportional to I square, correct? Theta proportional to what? Sorry, TC proportional to theta, correct? Or I can say that theta proportional to I square. What for? For what, my dear? For DC. What happens when AC is passed? So I can conclude from here that's non-uniform scale, non-uniform scale. Then what happened when AC is passed? Let's check that also. Let us check that also, my dears. What happened when AC is passed? Okay. What happens when AC is passed? Okay. So we have TD equal to what, my dear? I1 into I2 into dm by d theta. Am I correct? I1 into I2 into dm by d theta. Okay. So let I1 is equal to, my dear, Im1 into sine omega t, and I2 is equal to Im2 into sine of omega t minus phi. Let us, I am considering two currents, my dear, because I will tell you why I took this Im1 sine omega t and another Im2 sine omega t minus phi. I will tell you the reason. See, my dear, Im1 is nothing but the maximum value of first current, right? Im1. See, the I1 is current which is flowing through the what? Current coil. I already told you the current coil is fixed, very fixed, and it contains very less number of turns and very thick conductors are there, which means there will not be any that much inductance. But in the case of I2, what happened, my dear? In the case of I2, this I2 contain, or the current I2 is flowing through a very fine wire coil. A very fine wires it is flowing through, which means it is a moving coil or it is a pressure coil. Since it contains very high number of turns with a very least thickness, what happened? The inductance will be very high. That means always the current through that coil will be lagging with respect to the current through the first coil by some angle. If ideal it will be 90, the phi will be 90 minutes, but it won't happen. But generally what happen, I2 will be always lagging behind I1 by a certain angle. That angle is called this phi. Or I can say that what is this phi is equal to? Phi is nothing but, my dear, is phase angle between I1 and I2 symbol. What is I? Phase angle, phi is equal to what? Phase angle between I1 and I2. The angle which between I1 and I2 is called phi. Okay. So substitute this in TD. So TD will be equal to what, my dears? I1 is nothing but Im1 sine omega t, and it is Im2 sine of omega t minus phi. So I am going to multiply and divide with the 2. Multiply and divide with the 2. Is there any problem? Here I multiplied and divided. So I took this as Im1 by 2, Im2 divided by 2 into 2 into sine omega t into sine of omega t minus phi. So it will become, my dears, Im1 by root 2 into Im2 by root 2 into 2 sine A sine B. What is that? Cos of A minus B minus cos of A plus B. Am I correct? Cos of A minus B minus cos of A plus B. So this Im1 by root 2 is nothing but IRMS. Let be capital I1. Im2 by root 2 is nothing but, my dears, RMS value again, which is equal to I2 into what? This is just real. Okay, I will answer in one more extra step because you have a better idea. This deflecting torque contain T terms, my dear. If it contain T terms, means this deflecting torque is nothing but instantaneous torque, because it contains T. Time is varying, of course, so it is called the instantaneous torque. The instantaneous torque now, it won't produce any deflection, because instantaneous means it is varying. It won't produce any torque, but the resultant torque is always the reason for the deflection. That is called the average torque is always reason for the deflection. So average torque is the reason for the deflection. So did you know this? I hope that is also, because in YouTube now you can pause and you can write it. So the average deflecting torque TD will be equal to what, my dear? What, my dear? It is nothing but 1 by T integral 0 to T into TD instantaneous torque omega T dt. TD omega T. Okay, that means simply we integrating the instantaneous torque as an average, right? The average value is nothing but 1 by T into 0 T into V of T dt. Am I correct? So root square means what is root of 1 by T into integral 0 T into V square of T dt. Am I correct? So the average value will be equal to what? 1 by T integral 0 T into this by T. Here time bit is nothing but, my dear, 0 to 2 pi. Am I correct? Am I correct? And 0 to 2 pi into TD, it contains two terms. So can I write like I1 into sine of omega t into I2 into. So we what already expanded, right? We already expanded, right? Sine A sine B cos A minus B na. So I can write like that I1 and I2 you can take it outside. So I1 and I2 you took outside. Okay. So remaining term will be, my dears, cos of 2 omega t minus phi minus cos A minus B na. So initially it will be cos phi, correct? Minus cos of A minus B by A minus B minus cos A plus B. So 2 omega t minus phi. So what is this? Is integration with respect to d omega t. With respect to d omega t. Okay, my dears. So it will become I1 I2 divided by 2 pi into integration from cos phi, integral 0 to 2 pi cos phi is what? It's a constant na? So you can take it outside. So I can split this integration as two part. Okay, I can split this integration into two parts. I1 I2 by 2 pi into cos phi minus I1 I2 divided by 2 pi into integral 0 to 2 pi what? Cos of 2 omega t minus phi d omega t. I split it into two parts. So it will become, my dears, I1 I2 divided by 2 pi. What is integral 0 to 2 pi cos phi? It is the cos phi is constant here na. The constant, this is d omega t with respect to. So the cos phi is constant, you can take it outside. So integral d omega t, what is that? Yes, of course, of course. Of course, yes. So it will become, what is that? In the 0 to 2 pi integral d omega t is nothing but omega t, correct? Correct, na? So substitute that equation 0 to 2 pi minus I1 I2 divided by 2 pi integral 0 to 2 pi cos 2 omega t will become integral cos theta is sin theta. If you put the limit from 0 to 2 pi, sin n pi will become 0. So this need not to calculate this session, it is 0. So simply this one will be, so it is nothing but, my dear, I1 I2 divided by 2 pi, okay, divided by 2 pi. The dm by d theta is there, na? Dm by d theta is always there, okay, don't forget that. Dm by d theta is always there, don't forget that, okay. Dm by d theta is always there, na? I1 I2, right? I1 I2 into dm by d theta, correct? So dm by d theta is always there with it, and it will become, my dears, cos phi into this 2 pi into dm by d theta. This d theta is nothing but the deflection, and m is the mutual inductance. M is nothing but the mutual inductance. Okay, this is nothing but the deflection or deflecting angle. Phi is nothing but the phase angle, my dears. So this 2 pi and this 2 pi cancel. So the average deflecting torque will be equal to I1 into I2 into cos phi into dm by d theta. This is very, very important relation. Only this equation you can by heart this. No need to derive or no need to remember all this, but you may have an idea how it is obtained. So easiest derivation and all we can done by in our classroom, because it is easily understandable. But if the derivation is very big, especially in electromagnetic field theory, I will take after few days, that contains very huge derivations, very huge derivations. So deriving all these factors or all these things in the classroom, definitely one subject need at least 3 to 4 months. In that way you study, right? For for semester, for each semester you need certain subject, right? So if you spend 1 hour per day for one subject, how much time did you take that? Did you take at that time? You took 6 months. That means the whole semester you took in order to complete a session for one subject, na? So that much time is not there, and also that is for university examination point of view. But as for competitive examination, this derivation is not needed. But for your understanding, I simply told this thing. You just remember the average torque is equal to I1 I2 cos phi into dm by d theta. In the case of DC, it is simply I1 into I2 into dm by d theta, or I square into dm by d theta. Now I1 into I2 into cos phi into dm by d theta. So why I took I1 and I2 separately? Did you get the idea? In order to represent the two currents having some phase angle. For representing that, I took I1 and I2 separately. Okay. Otherwise, I can took I. Simply I can took I, na. So why I didn't? So that is the reason. Did you get, my dear? Did you get? So it is the deflecting torque. And one more thing, damping here we are using air friction damping we are using here. Only these return terms, now that is very, very important. No need to focus very much. And one more thing, for voltmeter, ammeter, scale is non-uniform, and for wattmeter, scale is uniform. This thing you have to note. The scale non-uniformity is for just voltmeter and ammeter. If this electrodynamometer type instrument is accommodated with, or this is used as a wattmeter by adjusting something in the load side or some arrangement, circuit arrangement. If you adjust something, it will form as, it will modified as a wattmeter also. So when we are using electrodynamometer type instrument as a wattmeter, the scale is uniform. That means it will give you the, because wattmeter means what, my dear? The power, it will give you the active power. Active power is not a squared quantity. Active power directly it will give. So the deflecting torque is directly proportional to the power, not a power square. So power is not, simply power means we can conclude it as a linear scale thing, right? It is a linear scale thing, not non-linear scale thing. Is it clear? Is everything clear? So that torque equation and certain things now, air friction damping, correct? Air friction damping, spring control, and the deflection torque in AC and DC cases. These are the things you just have to note, and the torque equation is very, very important. These two equations are really important in this section. Nothing more, nothing less. Is it clear? Is it clear? Is everything written on the board is clear to you, my dears? Is everything written on the board is clear to you? Okay. And one more thing we can write here. Used as this electrodynamometer means used as or used at wattmeter, voltmeter, power factor meter, ammeter, correct? Ammeter, energy meter, measure, etc. Is it here? So just read it. Okay, this can be accommodated with anything. Okay, voltmeter, ammeter, wattmeter, voltmeter, ammeter, wattmeter, measure, energy meter, anything you can accommodate with. But the important thing is that voltmeter and ammeter, the scale is non-uniform, but for wattmeter the scale is uniform. That only you have to remember. Okay, my dears. And very less sensitivity. Regarding sensitivity is very low. Sensitivity is very low. That also you can think. Okay, can I rub this? Can I rub this? Is it clear, my dears? Next, measurement of resistance. Measurement of resistance. Listen, my dears. So, resistance are classified into three types: low resistance, medium resistance, and high resistance. Low resistance, medium resistance, and high resistance. Low resistance is nothing but less than 1 ohm. Less than 1 ohm is considered to be low resistance, and medium means 1 to 100 kilo ohm. And high resistance means greater than 100 kilo ohm is considered to be the high resistance. So for measuring low resistance, my dears, for measuring low resistance, we have Kelvin's double bridge, and potentiometer method. For measuring medium resistance, we have Wheaton bridge, voltmeter method, ammeter method, voltmeter, ammeter method, voltmeter, ammeter method, substitution method, ohmmeter, and carry Foster bridge. For measuring high voltage means you have mega ohm, direct deflection method, and direct reflection method, and loss of charge method. A 1 mark question is there, sure, from this, just these things. You have a clear idea of what are the bridges and what are it's used for, what are the purpose of those bridges or those instruments. You should clear idea. Just by heart this, definitely you will get 1 mark. Definitely you will get 1 mark. Okay. Western, voltmeter, ammeter, substitution, ohmmeter, carry Foster, mega ohm, direct deflection method, loss of charge method, etc. Okay, you will get one mark from this. So these are the resistance ranges and these are the bridges. Okay, we don't want to study fully we don't want to study, but some bridges are we already studied now. Voltmeter, Western bridge you already studied, right? And something we will study now, some important things we will study now. Rest of all we not need to study all these. If you get time you can study, but not needed, right? Not needed, that's why. So I will take one by one and very important ones. Okay, I will take very important one by ones. First of all, voltmeter ammeter method. That's very important, that's why. Voltmeter ammeter method. In which case 1, ammeter is near to load. Okay, so we have to discuss it with the 2 cases. First one, ammeter is near to load condition. That means our aim is nothing but, my dear, by using a voltmeter and ammeter we have to calculate the resistance, that's all. The resistance value will be nothing but V by A, that is the measured resistance or the measured resistance will be nothing but V by I. Measured resistance is nothing but, my dear, V by I. Let be RA, not RM, RA. RA is nothing but the ammeter resistance. Okay. Measured value of resistance equal to V by A, which is nothing but RM. Measured value of resistance is nothing but V by I, which is nothing but, my dear, RM. That is nothing but, when we are applying a voltage, due to that there will be a flow of current. Simply V by A will give V the value of total resistance on that region, right? Total resistance on this region, you will get V by A will give total resistance in this region. That is nothing but the measured resistance, let it be RM. And initially you will have confusions. Array sir, what are you doing? To where you are going? Okay, finally it will be clear. Listen. So I can write, my dear, let IA nearly equal to I itself, because the voltmeter having very high resistance. So I neglect this current, small current IA, I mean the through the voltmeter, so that this I will be exactly equal to IA. That's nearly equal to IA. Thus IA will be equal to nearly equal to I. Why? Because this voltmeter having very high resistance, so it is likely to be an open circuit condition. Okay, and the meter is near to this ammeter. That means the resistance is near to ammeter, where RT is nothing but the true value, my dears, true value of the resistance. RT is true value of the resistance. Suppose it is given, you took 1 kilo ohm from the box. Okay, 1 kilo ohm. Array, let us find what its resistance by using voltmeter ammeter method. Is it 1 kilo ohm, or it is less than 1 kilo ohm, or it is greater than 1 kilo ohm? Let's check. That is this method, that's all. You already have a value of resistance, my dears, RT, true value. You know that value, but you have to check it by voltmeter ammeter method. What is the value of that resistor, RT? Whether it is increased, whether it decreased, or same. You have to check now. That is why we are using. So let I equal to IA, IA equal to I, so that I can write like my dear, V is equal to I into RA plus RT. Am I correct? V is equal to this IA equal to what? Nearly equal to what, my dear? I itself. So I into RA plus RT. V is equal to I into RA plus RT, or V by I will be equal to what, my dears? RA plus RT. What is V by I? RM, which is equal to what? RA plus RT. Which means what? The measured value is actually not the true value resistor. It is actually greater than the true value we obtain. Why? Because there is RA in series with the test resistor, true value resistor. Along with this true value resistor, there is RA also. That means if you simply take V by I ratio, the total resistance you got it is not actually, it is due to RT, but the small resistance offered by this RA also. So what will be the error? Error will be equal to what? Measured value minus true value divided by true value into 100. It's the percentage error, my dears. So it is again, what is measured value now? RI plus RT, correct now? Minus RT divided by RT into 100. RT cancel. Everything plus or minus, na? Plus or minus. Very, very important. Percentage error in voltmeter ammeter method, that too the ammeter is near to load end, means there will be error due to the ammeter resistance. That error is RA by RT, plus or minus RA by RT. Error will be there due to the ammeter resistance. While measuring the true value of resistance or test resistance, we will face an error which is nothing but plus or minus RA by RT. You just remember this. In case of ammeter, suppose ammeter is near to load, then it will plus or minus RA by RT. That's where RA is the ammeter resistance, RT is the true resistance, my dear, true resistance. And this much error will be there in the what? Measurement. Is it clear, my dears? Is it clear? Okay. Next, case 2. Voltmeter is near to load. What is that? Voltmeter is near to load, my dears. Now I can't simply neglect my voltmeter having very high resistance, and simply I neglect here means it will again give you the same effect as that of this one. It will again give you the same error as that of in ammeter error. So our aim is to find the error due to that voltmeter also we have to find now. So we can't neglect that voltmeter. We can't say that that voltmeter carries no current. If I assume like that, it will be an ideal voltmeter. Here we assumed because we want to find our area of concentration is on the load side ammeter, then what will be the error due to that ammeter? That was our aim. But now our aim is load side, there is a voltmeter, and what is the error due to that voltmeter? That's our aim. That's our aim. Load side, there is a voltmeter, and what is the error due to that voltmeter? That we have to find. So if we neglect that voltmeter means we can't find the error. We can't find the error. So that is the reason why we took separate conditions. We took separation condition, my dear. We took separate conditions. Is it clear? Is it clear? Initially, at the first time, if you see this, you may feel slight difficulty. If you study or if you revise it for 2-3 times, it will be easy. It will be easy. And nothing but difficult, my dear. You just remember this equation. That's all. Plus or minus Ra by RT. And for voltmeter also we will derive now. That also you just remember that two equations. Bus. Cinema over. Cinema over. Okay, my dear. So let's do that also. Okay. Tell me, my dears, what is I2? I2 I can write like I2 equal to what? Or simplify. What is RT here? Directly you can write like RT equal to what, my dear? V by I2. Am I right? Like this? RT is the resistance, is nothing but voltage across this. This is V divided by current through it at V by I2. R equal to V by I. Correct now? So it will be V divided. What is I2? I minus I1. So it will be nothing but V divided by okay. Let the voltmeter resistance is RV. Okay, my dear. Let voltmeter resistance be RV because we are focusing on voltmeter now. Should consider the voltmeter. So it will be, my dear, I minus what is I1? It is nothing but V divided by RV. Am I correct? Am I correct? Which is nothing but V divided by, take I from here. So I into 1 minus V by I into RV. Am I correct, my dears? So what is this V by I? It is the measured resistance all the time. If you simply take V and take I and take V by I ratio, you will get a resistance value which is nothing but the measured resistance, which is exactly not equal to the true resistance. It may less or increase. That is you have to find now. So this V by I is nothing but, my dear, measured value of resistance is Rm. 1 minus, what is this V by I again? Rm divided by RV. Oh, how beautifully we got it, right? So this is nothing but RT. So what RT. Okay. Okay, my dears, did you get that? Again you can go for the percentage error, which is nothing but, my dear, Rm minus RT divided by RT into 100. RT into 100, you will get a result like RT by RV plus or minus. It is again plus or minus. It's nothing but, I will write here, okay? Plus or minus RT by RV. Plus or minus RT by RV. Okay. You can solve by yourself. Take Rm minus RT. RT is, let's say like that. RT is like this one. Rm you put simply Rm and you simplify, you will get simply RT by RV into 100. So listen, my dears. In this, suppose the ammeter is near to load means it is Ra plus or minus Ra by RT into 100. Percentage error means it's 100. And suppose the voltmeter is near to load means it is plus or minus RT by RV into 100. See the opposite case. Okay. And see my dear, suppose this error will be minimum when this RT is maximum. Am I correct? This error will be minimum when denominator is maximum, which means it is suitable for low and medium resistors. So maximum, RT is maximum now, error will be minimum for RT is maximum now. So suited for medium and high value resistor. And see here, the beauty here, it is RT by RV. For this the error will be minimum when RT is very less now, very less. Suppose RT is low means percentage error also low. So this is suitable for low and medium value resistors. Suitable for low and medium value resistor. Okay, did you get that? Can I rub this? My dears? And the beauty here is that if you do this in case 1, that is error in case 1 equal to error in case 2. Is that clear now? Error in case 1 will be equal to error in case 2, because once you found in one way and in other way you are doing, you didn't change the meter and all now. So the error in case 1 equal to error in case 2, which means my dear, plus or minus RA by RT will be equal to plus or minus RT by RV. Correct? Where RA is the ammeter resistance, RV is the voltmeter resistance, which means plus or minus will cancel. RT will be equal to root of RA into RV. Very, very, very important relation. Very, very, very important relation. RT is equal to root of RA into RV is the true value of resistance, or the true value, simply true value of resistance by using voltmeter ammeter method. So in the examination, only the resistance of voltmeter is given, only the resistance of ammeter is given, then you can find the true value or true value of resistance, which can be used by found by using that voltmeter and ammeter. This is not always true, this is if error in case 1 equal to error in case 2. If error in case 1 equal to error in case 2. Sorry, it is always not true. Error in case 1 equal to error in case 2. Because both meters are different, right? One having low value of resistance, another having very high value of resistance. So it will not be same. So if error in case 1 equal to error in case 2, if both the errors are same, then this equation can be easily applicable. This equation can be easily applicable. Is it clear, my dears? Is it clear? Okay. Is there any doubt? Is there any doubt? Next, substitution method. So substitution method is for what? Medium value resistance. Voltmeter ammeter method is for also medium value resistance. Draw the sphere, my dears. Okay, draw the sphere. Draw the sphere. Yes, my subscribers are really less. Okay, nearly 430 members are there now. So spread your contacts. Spread this knowledge to everywhere. I mean, everyone. If you I've already told you now. My wish. Spread to everywhere. Okay, true knowledge should be spread to everywhere. So that's my wish. So please share to all my dears. It's my request. Okay, so next one is substitution method. As the name insists, substitution means, I will tell you why the name substitution. By doing, we will test. Here, my dears, V is the voltage battery. RH is nothing but a rheostat. RG is nothing but a galvanometer. The deflection is given on that, right? The deflection is given on this galvanometer. Because it's DC now, we are using DC now, that's why. And RT is nothing but the true resistance or test resistance. Any name you can call, right? RT is the true value of resistor, and S is nothing but the standard resistance. Its value is known to you. And this switch can be moved to both S1 position and S2 position. Okay. Listen, my dears. Suppose initially the switch is in S1 position. That means the current flow is through this leg. The standard is not there, S is not there. Okay, so what happened? What is the value of see, listen, my dears, I can say like V is equal to, let I be the current, my dear, I into, okay, RH plus RG plus RT. Am I correct? V is equal to, let I1, let the current be I1. Let current be I1. Let initially the S1 now. So let that current be I1. So I1 into RH plus RG plus RT. Correct now? So V is equal to total current I1 into RH plus RG plus RT. This is for S1 position. And S2 position, my dear, V is equal to, again I can write like, suppose the switch is to S2 position, I can write like, let that current be I2, because the current of course vary now. This resistance and this resistance are not equal. So even though these two are equal, this and these are not equal. So the current the second time will be definitely changed. So I2 into RH plus RG plus S. Okay, that equation number 1 and equation number 2. Since the equation 1, 2, LHS are same, my dear, it's always V now. So RH is also same. RH is also same. Which means I can write like, my dear, I1 into RH plus RG plus RT equal to I2 into RH plus RG plus RS. Am I correct? Am I correct, my dears? Am I correct? From this, I1 into RT plus I1 into RH plus RG equal to I2 into RH plus RG plus S, simply S. Okay, from this RT will be equal to what, my dear? I2 by I1 into RH plus RG plus S minus what? I1 into RT equal to this minus this now. So RT will be simply RH plus RG. That's all. Did you get this equation? Simplify this, make RT alone. So RT will be equal to IT by I1 into RH plus RG plus RS minus RH plus RG. And here, see, my dear, the deflection theta 1 proportional to I1 and theta 2 proportional to I2. Am I correct? The galvanometer deflection, suppose in S1 position means it is proportional to theta 1. Suppose in S2 position means it is proportional to theta 2. So theta 1 and theta 2 proportional to I1 and I2. So this equation will become RT is equal to theta 2 by theta 1 into RH plus RG plus S minus RH plus RG. So what did you get from this, my dear? What did you get from this? If you have an unknown resistor in your hand, you simply connect like this, you will get the unknown value RT. If you simply know the deflections in two cases, theta 2 and theta 1 divided by RH, RG, S, all are known values. So you can directly find the unknown value. Here you substituted, right? LHS equal to RHS, right? So LHS will be equal now, so RH will be equal. So substituted in that way. Then you got this method, right? So that is why the name substitution method. That's why the name, my dear, substitution method. Okay. Just remember this. RT is equal to theta 2 divided by theta 1 plus RT plus RG plus RS, or standard simply minus RH plus RG minus RH plus RG. Okay, is that clear, my dears? Any doubt? Is that clear? Any doubt? So that's all for medium resistor important methods. For maximum resistance or high value of resistance, loss of charge method. Just remember the circuit diagram ideas. Listen, loss of charge method is utilized to find, our aim is to find this R. This R may be an insulation or the insulation of a cable or anything, any high value for or rubber. What is the resistance of a rubber? It's a high value resistance, so you can find using this loss of charge method. So the method here is make the circuit diagram like this. First, make the switch close at t is equal to 0, t less than 0, switch is closed, and allow this capacitor to charge up to a voltage Vc, and at t is equal to 0, my dear, switch open and allow the capacitor to discharge through this R. Note down the time for the complete discharge. Then the value of R will be equal to C log 10 V by Vc, 0.4343 T divided by C log 10 V by Vc. This equation gives you the value of the high value resistor R. The high value resistor R, 0.4343 T divided by C log 10 V by Vc, where V is the applied voltage, Vc is the voltage across the capacitor, T is the time for that discharge, and log 10, C, okay, C all or no, You just remember this equation. No one will ask you the derivation, how that equation arrived, and no one will ask you. Okay, so that is loss of charge method. Next one is Megger. Of course. Did you see the Megger diagram, my dears? If I draw this Megger diagram, it will full of this screen. I mean, in this board. Beyond that, it will go sometime. Did you see that Megger tester? You just check it, Megger. It's a combination of two generators. Okay, combination of two generators, and one is like act as a generator, and other one is act as a motor. Okay, and it's a very, very big figure. So we don't want that construction and working and all. We just need what? Some important coil. It is operated at 100 volt. It is run at 160 rpm. Megger is run at 160 rpm. It is a generator now. My dear, that's principle is simple. You allow to pass certain current through the insulation and find the current value. Just note the current value. V by I will give the value of resistance, that's all. V by I will give the value of resistance, that's all. Okay, and which is used to measure high resistance. Used to measure high resistance. Air friction damping is used. Air friction damping is used. And control torque not by a spring but by a coil. Very, very important. Used to measure insulation resistance, resistance of UG cable, etc. UG cable. Just note this point, that's all. Nothing more, nothing less. Okay. Is it clear, my dears? Is everything okay? So that's all for today. Let's meet again tomorrow with a new session. Until then, bye. Take care.